Happy Friday.
Yeah, I'm one of the worst procrastinators ever. If there was a knitting homework, I'd just ride that boat.
We're finishing up the 3.1 notes with the graphing calculator problem. So instead of using like our little candidates test here to locate our absolute extrema, this one says use a graphing calculator to graph the given function and find the absolute extrema of the function on the given interval. Okay, so let's go ahead and type this function into our y equals. So I have negative x, make sure you're in radian mode, plus the cosine of 3 pi x. Now we're only looking from 0 to pi over 6, so I'm going to change my window so I don't get confused on anything outside of my range here. I'm going to change my x min to 0 and my x max to pi over 6. And then for y minimum, I'm not quite sure how low or how high. Well, actually, I do. It's a cosine curve, right? So it's not going to go much over 1 or negative 1. So let's just kind of maybe do negative 2 to 2. Oh, oops. I didn't type that in right. Negative 2 to 2. Sorry. Let me get that fixed there. There we go. Okay. So remember, for absolute max and absolute min, we're looking at all the critical numbers, which include horizontal tangents, so pits and peaks. And we're looking for any parts where we're not differentiable, so any corners, cusps, discontinuity. We don't have that case here. So I do see that this endpoint right here looks like it's my highest value. What we can do is we can kind of hit that trace button. And you can just kind of toggle along the curve here and figure out what do we have a value of right there at my endpoint. And right at 0, I see I have a y value of 1. And obviously, like, this dips down below my x-axis, so that's going to be my absolute max. You can just kind of use the trace button to find that when you have an endpoint. Use the trace button. Okay, for the absolute min, though, I see it looks like it's located down here where I have a horizontal tangent. So it's kind of inside my interval. It's not an endpoint. I forgot what I call those ones. What do I call those? Interior points. That's what I mean. Interior point. Okay, so your calculator does have an actual button to calculate these mins and maxes. So if you hit second calc, a minimum, number 3. And I think we've used this tool before, but you're just going to toggle over. It says it's going to ask you left bound question mark. So you just need to go to the left of that minimum. Keep going, keep going, keep going. Hit enter, and then it's going to say right bound question mark. Hit enter. It'll say, do you want me to guess? Yes. Hit enter one more time. Yep, I can do that. Second calc minimum, which is option 3. Left bound, so you just need to toggle to the left. Enter. Right bound. Enter. You want me to guess? Yes. Okay. So obviously my calculator is only going to give me rounded answer. It's not going to get my exact, like, in terms of like pi, and that's okay, because they're telling you can use a graphing calculator. So if I were to make a table for this, I see that I obviously have my endpoints of 0 and pi over 6. And then the only critical number here I have is this minimum. There's no other pits or peaks. There's no other types where it's not differentiable. So that interior point I'd probably put right in the middle of my table there. That's 0.3446, dot, dot, dot. And I got a value of negative 1.3389, dot, dot, dot. This one we got 1 for that endpoint of 0. Now I can tell from my graphing calculator that my right endpoint is not an absolute extrema here, but for sake of filling out our table, we can go ahead and toggle over there and see what we are at pi over 6 at our endpoint. Oops. Or, even better, you can go to your table and you can type in, we have that 0 endpoint, we have pi over 6 if you want to know exactly what it is at pi over 6. I have like negative 0.3030 for that endpoint. Okay, so obviously I have my max here. My absolute max. And my absolute min here. So when you're doing the endpoint ones, if you can't tell exactly what it is, so I used that trace button to get to here, but like that pi over 6 one, if you can't tell exactly what it is, then go to your table and type in the endpoints and get like the exact values. Okay. As a refresher, remember you can also, anytime you have something typed into your Y1, if you want to evaluate it, you can hit that alpha trace button and this menu will pop up and you're like, okay, I want to evaluate this function at my endpoint of 0. It'll tell us 1. Alpha trace, my other endpoint of pi over 6. This is the same as using the table, but this might be a little bit quicker. We get that number as well. All right, but I just didn't have to algebraically find my critical points.
How'd you get the Y1 again?
Alpha trace. And this menu will pop up, and then you just hit enter. And then any interior points, you can use that utility of the calculating either the max or the min. And the same would work for the maximum that we do with the minimum. Pretty nice. Okay. That's how you use your graphing calculator on those problems. And that's 3.1. Yay. All right, I'm going to pass up the 3.2 notes. Say a little warm up for you to do. One graphing of just determining the critical numbers. One algebraic, where I want you to find the absolute extrema. All right, I'll just give you a couple minutes to try those problems. give you about 1 more minute. Okay. On the first one, determine the number of critical numbers for the function below. So remember, our critical numbers can occur at 2 points. When our derivative is equal to 0, horizontal tangents, which are mins and maxes, or where our derivative doesn't exist or is undefined or we are not differentiable. So there was 3 in this case. There was 1 with a horizontal tangent. That was right here. I'm just going to list the x values. If you listed the ordered pairs, that's okay. So -3 would be a critical number. And then there were 2 spots where my derivative does not exist, and that would be at this cusp and at this point of discontinuity. So x equals -3, -1, and 3 would be my 3 critical numbers. Okay. Questions on that? Kind of a fun problem. Next one is just like the ones we practiced a bunch of in the notes, where we algebraically had to find the critical numbers. Handwriting looks better. So determine the absolute extreme, and this is like that candidate's test. Basically, you have to find critical points. I found 2. So start finding the derivative. Like I just said, when is my derivative equal to 0? When I have horizontal tangents, it'd be at x equals 1. If it helps you with rational exponents to write them as radicals, that's really like a cube root of x. If that helps you to like algebraically solve it, you can do that. I just keep everything rational exponents. And then I also had a point where my derivative was undefined or didn't exist, and that was when my denominator was 0, and that'd give me an x value of 0. Both of those are in my interval. So when I go to make my table, I need to test my endpoint -1, my critical point of 0, and then my critical and endpoint of 1. All right, when I plugged -1 into here, I got 5. 0 is obviously 0. And when I plugged in 1, I got 1. So -1,5 would be my max. I'm going to write it. And 0, 0 would be my min. Okay, so my curve has an absolute max of 5 when x is -1, absolute min of 0 when x is 0. Okay, how do we do? feel like it's a little algebraic and not too complicated, but makes sense too, what we're doing. Okay, this next lesson is pretty much 2 theorems we're going to learn. One is called Rolle's theorem, and it's not one of our big 3, but it'll help us understand the mean value theorem, and this is probably the most important theorem that we're going to learn all year. I don't know if we'll quite get to it today. Might have to wait till Monday, maybe a little bit. But Rolle's theorem kind of helps us understand the mean value theorem. So we're going to start with this one. This one's not tested on the AP exam. But the mean value theorem is one of our big 3. It's our last of the big 3 we have to learn. It'll kind of help us, like I said, discover why this mean value theorem works. Okay, and that's all the lesson is. It's really just a couple of these theorems, and it kind of plays off of these mins and maxes, these extrema. So we're going to start by doing this little activity, if you will. It says, consider the values of a differential function f of x in the table below to answer the questions that follow. Plot the points and connect them on the grid below. Okay, so I know your grid's kind of tiny. Sorry, I screenshotted it and it turned out to be a little bit smaller than I thought. But let's go ahead and plot these. 0, 1, 2, 5, 4, 8. Back when math is easy, just plotting points. 6, 10, 8, 11, 10, 10, 12, 8, 14, 5. It's looking very symmetric, looking like a parabola. 16, 1. All right, connect these in a smooth, continuous curve, and don't do arrows because we're going to keep these as like endpoints. We're just going to look at this interval 0 to 16. Okay. So, in calculus, the derivative has many interpretations. Something we talk about a lot is how it's really like our rate of change or like our slope of a function, right? So we've really hit on 2 rates of change. So this is just a little review. Average rate of change over an interval, which I often abbreviate as AROC, is where we take one endpoint and a different endpoint, and we essentially just calculate the slope between those. So we do like f of b minus f of a all over b minus a. So what you're really finding when you're finding the average rate of change is you're finding the slope of a secant line. Secant line meaning it passes through 2 points and it passes through like the 2 endpoints. Okay, that's average rate of change. We've been doing that since like the first day of calculus. So here's a little example underneath it. It says find the average rate of change on the interval from 2 to 12. So from 2 to 12, if I wanted to find the average rate of change, that'd be the slope between those 2 points. So f of 12 minus f of 2 all over 12 minus 2. Okay, if you want to draw the line, you can, but this would be a secant line because it passes through 2 points. I can do a good job here. Oh, that's pretty good. All right, so f of 12, you can obviously get that from your table or from your graph. That's 8. F of 2 is 5 all over 10. 3/10 would be the average rate of change between those. Makes sense because we got a positive slope and our secant line's clearly positive. Average rate of change. Okay, you guys have been doing that since Algebra 1. Now, what calculus allows us to do is find the instantaneous rate of change, which I often abbreviate as IROC, and that's the rate of change at an instant at a specific point. So let's just notate this as like f prime of a. the derivative at a specific point. And we know that this is the slope of a tangent line at the point x equals a. Okay, those are basically our two big rates of changes that we talk about with derivatives. So their kind of example question for this one is the instantaneous rate of change of f at x equals 4 greater than the rate of change at x equals 6. So if I were to look at my graph here and try my best to draw like a tangent line at x equals -4, it would look something like this. Tangent meaning only hits my curve in one spot. If I were to draw it at x equals 6, this point right here, and follow the curve, my tangent line would look something like that. So what do you guys think? From those tangent lines, is my instantaneous rate of change at 4 greater or less than what it is at 6? Greater. Why?
Steeper.
Exactly. The line's steeper, right? That tangent line's steeper. So that slope is going to be like greater or like faster, that instantaneous rate of change. So we can just say f prime of 4, that instantaneous rate of change at 4, is greater than the instantaneous rate of change at 6 because the tangent line is steeper at x equals 4. Good. Okay. I love this because A, it's going to help us see this Rolle's theorem in a second, and B, it's such a good review over those rates of change, which are so important. This is like the whole first semester of calculus that we talk about these rates of change and applications of them. All right, so here's Rolle's theorem. And it feels like it's kind of like common sense, but I like it because obviously it ties in like some calculus for us. If we have a continuous function on a closed interval, and it's differentiable on the open interval, meaning no cusps, no corners, no discontinuity. Well, that's takes care of in our first statement there. But if it's differentiable on that same interval, if the values at my endpoints are the same, so like the heights of my graph at my endpoints are the same, then there's at least one number in this interval where we have a horizontal tangent. Okay, where the derivative, the instantaneous rate of change at that point has to be 0. So think about it. If you had two endpoints, and you had to connect these dots in a continuous differentiable fashion, I mean, we could draw a straight horizontal line, but then I have a constant rate of change of 0 at every single point, right? That's at least one. The only way I could connect these two dots, at some point, I would have to have like at least one horizontal tangent. That's what this Rolle's theorem says. Okay, so if we look back at this example, Rolle's theorem would apply because look at my endpoints here. So on that closed interval 0 to 16, is my function continuous? Yes, I can trace it without picking up a pencil. Is it differentiable? Yes. F of 0 is the same as f of 16. Those outputs are both 1, so Rolle's theorem would apply. That there has to be at least one point where you have a horizontal tangent. Whether it's a max or a min, we don't know, but there has to be at least one point where we have a horizontal tangent as long as our hypothesis is met, meaning continuous on the closed interval, differentiable in the open. Okay, so for Rolle's theorem, here's what I would write. Again, this isn't on the AP exam, but on your homework, you must state, in order to use this, you must state or like show two things. One, that your function's continuous. on the closed interval. So obviously you can kind of see this pattern, like anytime we have theorems, we have to show their hypothesis holds. 2, f is differentiable on the open interval a to b. And then you also have to show that the heights or the outputs of your inputs are this, of your endpoints, yeah, I guess endpoints, the parts on your interval, the endpoints are the same. Otherwise, we can't use Rolle's theorem. So we must state that in order to show that there exists at least one x equals c such that f prime of c equals 0, such that we have a horizontal tangent. It's pretty much what that means. Okay. So we must state that it's continuous, differentiable, the outputs are the same in order to use a conclusion of this conditional statement. So if it's continuous and differentiable, and if the outputs are the same, then we can conclude there is at least one number in the interval that has a slope of 0 at that instantaneous rate of change. Okay, make sense? We're only going to do 2 examples with Rolle's theorem, and then maybe we'll say mean value theorem for Monday. We'll see. Okay. Determine whether Rolle's theorem can be applied to f on the closed interval a to b. If Rolle's theorem can be applied, find all values of c in the open interval a to b such that you have a horizontal tangent, f prime of c equals 0. If Rolle's theorem cannot be applied, explain why not. Okay, here I have a nice polynomial function on the interval -3 to 0. So first thing I have to state is that it's continuous on the interval. And since it's a polynomial, it's going to be continuous everywhere. So G is continuous on -3 to 0. Also, since it's a polynomial, it's differentiable everywhere too. Okay, so remember when you're stating if it's differentiable, you have to do the open interval, because we technically don't have, I guess I could do this interval. This is a degree 4 or something like this. Well, oh shoot, it has a negative leading coefficient. Let me draw a more accurate graph of what this might look like. Something like this. So -3 to 0, technically at endpoints, we don't say it's differentiable there, because coming in from the left and the right have to be the same thing, and there doesn't exist anything over there, so you just have to change the interval to the open interval, because technically we don't have derivatives at that specific endpoint. So just make sure when you're stating if something's differentiable, you always use the open interval for differentiability, okay? All right, so the next thing we have to show before we can state if Rolle's theorem applies here, we've met 2 out of the 3 criteria for a hypothesis. We have to show that at our endpoints here, we have the same output. So I'm going to start by just plugging in g of -3. Okay, I got 0. So I have 81 minus 81. And then I'll plug in my other endpoint here of 0, which obviously there I get 0. Okay, so g of -3 equals g of 0 equals 0. So you kind of showed that third case scenario that Rolle's theorem will apply here. Okay, So what this allows us to do, I'm going to kind of come off to the right here now. What this allows us to do is find a value in this open interval, -3 to 0, where we have a derivative of 0. So we're just going to start by finding the derivative. Nice, easy polynomial. We get 18x minus 4x cubed. So what I want to do here, this is how I kind of show my work. I want to find the value of c. You don't have to change it to c. You could keep it as x if you wanted to, in which my derivative is equal to 0. And we're just going to solve for c. That's like the true notation of Rolle's theorem, is using those c's. Okay, so I'm really just solving this equation. I could start by factoring out a 2c. I get 9c minus 2c squared. Oh, not 9c, just 9. We factored out the c. 9 minus 2c squared. All right, so here, when 2c is 0, that'd obviously be when c is 0. Okay, I'm not going to circle that. We'll come back to that after we're done solving. And then we could also have this be equal to 0. Okay, I can solve this using square roots. We get 9/2 is equal to c squared. So c is plus or minus square root of 9/2, which I would just write that as 3 over root 2. You don't need to rationalize it, but you should square root 9 at least if you can. All right, so remember it says at least 1, so we can have more than 1. But we have to be conscious of what our interval is. So technically, Rolle's theorem says there exists a number c in the open interval. So if I get 0, that's technically not included in the open interval. So we have to ignore that one. That's technically not in our interval. Not in the open interval. And neither is which answer from here?
Positive 3
Positive. So we only do negative 3 root 2. That'd be my final answer. Usually I box my final answer and I fix that. Okay, good. There's an example of Rolle's theorem. We could look at this at a graphic calculator really quick, just to show you that time. So here is my polynomial. I only want to look from -3 to 0. Okay, I'm just going to go back to my -10 to 10, just to see how that looks. Okay, we need to go higher. Did I do that wrong? Oops. 20. A little higher. 25. Okay. So in this interval, -3 to 0, you can see, we got those same outputs of 0 at our 2 endpoint. So we could use our grapher to determine if we got the right x value here. So we could go second calc, see if that maximum there, left bound, right bound, guess. -2.121, okay, remember that number. And then to get the decimal answer of -3 divided by root 2, you can see we got that same number. So we found the right one. Okay, we'll end on this next problem. So here I have g of x is sine of 2x divided by x plus 2. So the first thing I need to show is that it's continuous on the interval -4 to -1. But I look here at my denominator, and when my denominator is 0, my function's undefined at -2. Is that in my interval? Yeah, so automatically first hypothesis not met, since g is undefined at x equals -2. G is not continuous. What type of discontinuity would that be? Not a whole, because it doesn't cancel.
Horizontal.
Close. Vertical asymptote. Yep, so it'd be like that infinite discontinuity. G is not continuous. Now that wouldn't matter if it fell outside my interval. Okay. But in this case it does. Therefore, Rolle's theorem does not apply. Okay. That is Rolle's theorem. That's half our lesson. So like I said, mean value theorem is really important, so we'll stop here and pick this up on Monday when we're all very refreshed from the weekends. Second hour Monday morning. I do tentatively, well, I guess this is probably more solid now since I know we'll finish this Monday.